The other type, another type of detector, one that we actually are going to use in everyday practice, is called an optically stimulated luminescence detector, or OSL. These are your badges. Now there's different types of badges. This is one of them. So recall that X-rays are a form of potential energy. They carry the potential to deposit their energy into atoms. That's why we call them potential energy. If you build material in such a way that you can capture the energy and store it, then later on you can use later on, if you design this right, you can have a way of causing the material to re-emit the energy that it absorbed, and you can measure that later. Okay? So crystals are going to work great for doing this, because crystals have this special structure, atom structure where they can trap electrons. But quartz or feldspar crystals, remember those materials, they can store energy absorbed from X-rays and delay the emission of light until they are exposed to light. That's optically stimulated luminescence. Luminescence is the property where a material can emit light when it absorbs light. So it can absorb energy and then re-emit that energy. Optically stimulated luminescence is a material can absorb energy and then only re-emit that energy when you shine a special light on it. If this sounds familiar, it's the same as the photostimulable phosphor plates used in CR X-rays, computed radiography. So remember digital computed radiography? The CR plates use the same thing. It's the same type of thing. So again, remember, X-rays are potential energy. When they strike an atom, they deposit their energy into the electrons of the atom. An X-ray photon hitting an electron, what can it do to it? And that can make the electron do what? What was the question? So an electron, a little negatively charged electron orbiting an atom, if it is struck by an X-ray photon, what can happen to that electron? It can be ejected, right? What does that mean for it to be ejected? So the atom's ionized. What does it mean for the electron, though? Why was it ejected? Why didn't it just stay in place and just like jiggle around? Because you're giving it kinetic energy. Importantly, you're giving it enough kinetic energy to where it can leave the atom, right? How in the world did you give an electron kinetic energy? Because of the X-ray that was shooting into it? Yeah, you let the electron absorb an X-ray photon, okay? Now remember that electrons are bound to their atoms, okay? It takes a certain amount of energy to release an electron from an atom, okay? Let me give you an example. Can anyone remind me what the inner shell of an atom is labeled? What letter designation? K shell. So you have an atom, right? The atom's got positive charges and neutral charges in the nucleus, right? So there's a nucleus of an atom. Then you've got electrons in orbit around the atom, okay? And you might have, 1, 2, 3, 4. I just drew an atom, very poorly drawn, but I drew an atom, right? It has a nucleus there. The nucleus has protons and it's got neutrons. It's got a first shell of electrons with 2 electrons in it. It's got another shell with 6. I've crudely drawn what atom? If it's got 6 electrons, that means it's going to have 6 protons. Should be carbon. 6. Carbon should be 6. And I'm not being accurate at all to the periodic table right now because I'm going to use random binding numbers. But what's important here is that any atom, the electrons that orbit the atom are held in place. They are pulled on by the nucleus. Why? Why are these electrons being pulled by the nucleus? Yeah, opposites attract, right? So these are, so let's say, electrons are so like, you know that you can take something, right? Like my bottle, and I can kind of turn around in a circle. My bottle just kind of stays like that, right? If I turn around really fast in a circle, I can make my bottle sort of raise up like that and hold its line, right? I can make it, right? So I spin my bottle around, and my bottle stays like that. It sits horizontal, right? But if I go slowly, my bottle stays vertical, okay? Why did my bottle, when I spun extra fast, pull itself out like that, horizontal to the ground? Right. So if I go really slowly and flip this bottle over, all the water falls onto the lid, right? Okay. But if I go fast enough, the water stays in the bottom. What force is keeping the water in the bottom?
Gravity?
Not gravity, because when I go upside down, I can't start to freeze it in time. When I go upside down fast enough, the water stays up here, right? It's spilling anything, right? You can see what happened if I went a lot slower though, right? But if I go fast enough, I don't spill anything, okay? So it's not gravity, right? Because the water, when this bottle is upside down, the water's stuck up here at the top. There's a force doing that, right? What is that force?
Flat speed.
It's angular momentum, but that's not the force. The force is called centrifugal force. You guys have all heard of centrifugal force before, right? The tendency for something is to pull outward as you're spinning it, okay? So just showed you that with the bottle, like that, right? Okay. Atoms have the exact opposite force, okay? The electrons are attracted to the nucleus with something called centripetal force. Instead of centrifugal, it's centripetal. Okay, pedal means towards your feet. Okay, so like, imagine this was like the Earth, right? And the atoms are attracted to the surface of the Earth. Okay, so atoms hold their electrons in with something called centripetal force. Okay, and we say that the energy is in units of keV, kilo electron volts. So we say there's an amount of force given in units of keV holding an electron onto its atom. Okay? All right. I'm going to make up a number. Okay, so let's say this is true. Okay, so the K shell in atoms equals the first shell level of electrons. Okay, the L shell equals the second shell level. KLMNOP. Okay, for no good reason. K does not mean anything special. Just A, B, C, D, E were already taken. Okay, and we can call them shells 1, 2, 3, 4, 5, and 6, but we call them K and L. So the K shell is the one I'm going to talk about right now. That's the inner shell here. Okay, the K shell, the electrons in the K shell of any atom are held on tighter than the electrons in the L shell. Okay, so the atom holds on with more centripetal force to the K shell more than it does the L shell. Okay, we would say an atom, in its innermost shells, the electrons are held on more tightly than they are in the outermost shells. Okay, this is referred to as the amount of binding energy. Binding energy is given in units keV. Okay, and there's more binding energy holding this electron on than this one. Okay. And this, you can do this sort of intuitively with, this is not gravity that's doing this, but sort of you can do this intuitively with gravity, right? When I stand here on the surface of the Earth, right, I'm held pretty tightly to Earth, right? I can jump and I don't go really very far, right? Okay, but the International Space Station, orbiting Earth, right? It's in Earth orbit, so it's captured by Earth, it's part of Earth's gravity. You don't feel the gravity because you're in essentially free fall, okay, in microgravity. But you're feeling Earth's gravity. They are further away than I am on the space station, right? They're a couple hundred miles above Earth on the space station, okay? We both feel Earth's gravity, but I feel it more because I'm closer to the center of the Earth than they are, okay? That's why, one main reason why they feel more gravity than we do, okay? Or they feel less gravity than we do. I'm the inner shell, they're the outer shell, okay? Okay, so there's more binding energy holding this electron in than this one. I'm going to get back to this, I promise you, in a moment. Okay, so then a X-ray photon comes in, okay? An X-ray photon comes in, and it happens to run into that inner shell, okay? When we set settings, when we make settings on the X-ray machine, how do we set the energy? What factor do we change to set the energy of the X-ray beam? kV, right? So what's like a kV we've used before? 70, good. So when you set the voltage on the machine, you're setting what the energy will be in the X-ray beam, how much energy the X-ray beam will have. When you make a 70 kVp, sorry for my writing, 70 kVp on the X-ray machine, that means you're making X-rays from 0 all the way to 70. And anywhere in that range, okay? But let's, for the purpose of this, just say that if I set 70 kVp on the machine, this photon's going to have 70 kVp, okay? And kVp can also be expressed as keV. They're equivalent things. So 70 kVp setting can give you a 70 keV photon. That's the energy of this photon. keV, as listed over here, stands for kilo electron volts. Kilo for 1,000 and electron volts for energy. Okay. This X-ray photon, we're going to say it has 70 keV of what kind of energy? Or what kind of energy are X-rays? Potential, right? It has 70 keV of potential. What can it do with that 70 keV? Maybe. We're going to get to that. But that X-ray photon cruising through space, massless photon cruising through space, does it do anything until it interacts with something? But what moving through empty space? X-ray photon cruising through empty space. Remember, atoms are a lot of empty space, right? Even as I drew it, there's a lot of space where they wouldn't hit something, right? So you're cruising through empty space. Does an X-ray photon do anything when it's moving through empty space? No, that's why we call it potential, because it's not going to do anything with its energy until it interacts with something. An X-ray photon that doesn't interact with any air or anything else could in principle travel forever without interacting with anything, okay? But importantly, when it does interact with something, it can deposit, or said in the right way, convert its potential into kinetic energy of something else, okay? So remember, binding energy is listed in keV as well. So let's just, for the purposes of this, say that the amount of energy holding this guy in place is 60 keV. Okay, it's not in carbon, it's not 60, but the point is, I'm not drawing an actual atom. So this electron in the inner shell is held in with 60 keV. Okay, that means it's held on tightly with 60 keV of energy. If my X-ray photon comes in, deposits all of its energy into that electron, how much energy would it take to remove this electron? Well, it takes a minimum of 60 keV to remove the electron. Okay, these outer shells are held with less energy. So there might be, I'm making up numbers right now, but there might be 40 keV holding the outer shells in. Okay, so there's less energy binding the outer shells. It's easier to remove one of these outer ones than it is to remove this one. Okay, but this electron held on with 60 keV of energy. If you deposit 60 keV worth of energy into it, the electron will leave the atom. It is enough energy to break the bond between the atom and the electron. Okay? However, this photon has, just because we said so, has 70 keV of energy. Okay? So how much is going to be left over after that photon absorbs into that electron? 10 keV, right? So you deposit this photon into the electron. The electron then shoots away from the atom with 10 keV worth of kinetic energy. Okay? This is how the electron has absorbed the photon and carried away the excess energy. Okay, remember, energy is conserved, right? So you carry away the excess energy. So this electron is now going to leave the atom with 10 keV of kinetic energy. I'm not saying exactly how fast that is, but it's 10 keV worth, okay? If instead the incoming photon had 80 keV of original potential, how much kinetic energy would that electron end up with? 20. That means it'd be traveling faster, okay? And if instead of that, the original photon had 65 keV, that means the electron would leave with 5 keV of kinetic, okay? So it really is just that simple, okay? The more energy the photon carries, the more it can deposit into the atom, into the electron, and the faster the electron is ejected from the atom. Okay, this is the principle behind ionization, is just conservation of energy. Let me give you one more. What if instead of 65, if the incoming X-ray photon only had 55 keV of energy? Would we eject that electron? No, right? That electron would be happy in its place. Now what it would do is, the electron would increase in kinetic a little bit. It would raise up the shell level, and then subsequently jump back down to where it came from. And it would re-emit that photon back out of the atom at exactly the same energy. Okay? It would temporarily hold on to it, and then immediately shoot it back out. Okay? You have to go above the binding energy of an individual electron in order to eject the electron. That make sense? Okay, good. Now, moving back to this, okay? So, OSL detectors, they have a special crystal structure where when an X-ray photon strikes the electron and it has enough energy to eject it, the electron is ejected, but because of the crystalline structure, this perfectly arranged structure of these atoms, that electron doesn't get to go flying off into space like I indicated with this one, okay? That electron gets trapped, okay? And remember, it's holding on to however much kinetic energy it had, right? It's holding on to that, right? It can't let it go because it got trapped, and energy can't be lost, okay? So it gets trapped here. And remember, this is a big lattice, big matrix of atoms, and many, many of these are happening. It's not just the one here, but for the purpose of this, it's one. One photon ejects one electron, and it gets stuck because of the structure of these atoms. None of these other atoms can absorb that electron because they're all full. They can't hang on to the electron, and the electron is trapped now. So later down the road, you take off your badge, you send it to the badge company. The badge company puts your badge in a machine. The machine uses, in this case, visible light, optical light, visible light, to put energy into these atoms, okay? When it does that, this electron absorbs some of that energy. And to give a hand wavy explanation, the electron jumps out of its trap and back into the atom it came from. When it does that, it has to re-emit all the energy that it absorbed. Okay? And so it re-emits everything that it absorbed. All of the energy that it was holding onto gets re-emitted back out. Now, it's not going to come back out as an X-ray photon. It's going to come back out as several photons of visible light. All, if you added them all up, would have the energy of the original photon. Does that make sense? So we can measure how much visible light is re-emitted from the material. And from that measurement, we can say how much were you exposed to? How much got absorbed into that badge to begin with? Okay. This event to this event can be months separated. Okay, you wear your badge for 3 months. Okay, so this is happening the entire 3 months. And you send your badge to the badge company. The badge company takes and shines their special light at it and measures how much light your badge re-emits. Okay, and they can calculate from that how much radiation you absorbed. Okay, there's 2 types of badges that do this. There's the OSL badge. There is also something called the TLD badge, thermoluminescing detectors. They work on the same principle. The only difference is the type of electromagnetic wave that's used to cause stimulated emission once the badge is being read. In OSL badges, the companies will use optical light, visible light, to make that happen. The material is sensitive to visible light. In TLD badges, the material is instead sensitive to infrared heat. Okay? So let me show you TLDs. So let me just wind this up here. OSL badges that I just described are highly durable, can be worn for up to a year, but are often used quarterly. Okay. Packaging is impervious to light, heat, moisture, and pressure. That means they're not sensitive if you leave them in your car on accident, okay? As long as you have UV blocking windows in your car, okay? And they're not sensitive to if you run them through the washing machine on accident. So they're really, really resilient, okay? This high sensitivity and durability makes them very accurate. They can detect as low as a 10 microgray exposure. Micro is millionths, if you remember. And can be re-stimulated multiple times to confirm the original reading. So they can be checked and double checked. The only difference between OSL badges and these TLD, thermoluminescing dosimetry badges, is that the material is different and it responds to, instead of visible light, it responds to heat at the badge when it's got given back to the company. So you should remember, TLD badges use lithium fluoride as the material. They re-emit their energy when they are heated. And again, it's no mystery what heat is anymore to you guys. Heat is just electromagnetic waves, but at a longer wavelength than visible light. It's the same thing, right? Just a different energy. Same thing happens though. Upon X-ray exposure, ejected electrons are captured and stored in electron traps within the structure of the material. Same exact process. Just a different material and sensitive to upon stimulated emission, sensitive to heat instead of optical wavelengths. Any questions there? I mean, I'm sure there's something, but I want to make sure I iron out any big issues here. Okay. All right. Fantastic. You guys are doing great. This is a lot of super duper technical information, and you guys, I think, are handling it really well. So let's keep going. I want to get as far as I can through this stuff. Okay, so there's the next level of understanding to have is, okay, so you have badges, right? There's OSL badges and TLD badges. I haven't described film badges yet, but I don't think it's necessarily necessary. I may get to it. These two types, OSL and TLD badges, are the types that you will come in contact with. Okay. Any of those octagonal badges, or hexagonal, or whatever they are, I think they're octagonal. No, hexagonal, excuse me. Six-sided badges. Those look like a little stop sign almost. Those are all going to be OSL badges. Okay. Here at the school, your little rectangular ones, those are TLD badges. Okay, so they're the same type of thing, they just work slightly differently. What's important to know is all the badges will have what are called filters in them. Okay. At different spots on the badge, you're going to have different materials that the X-rays will have to pass through. Okay. Higher energy photons will penetrate further. Okay. The energy level and thus the type of radiation received can be determined by using various filters, such as simulated bone, aluminum, tin, copper, or areas with no filters at all. And they compare the ratios of exposure under these different filters, and something called the half value layer, or the energy of the beam, can be obtained from that. So not only can you determine how much exposure you were given, you can actually determine what energy level that exposure was at, effectively the type of radiation that the badge was exposed to. Which, if you remember from earlier, that will allow them to determine the dose equivalent, not just the dose, but the dose plus type of radiation. And you'll see on these pictures here that where the arrows are pointing, those are the filters. They're very small. So I think the arrow is indicating copper on all of these. So you'll see that brownish copper filter with the arrow pointing at it on all three of them. So each of these will have different filters. You'll have things for, we'll want to be able to simulate metal. We'll want to be able to simulate bone. We'll want to be able to simulate what soft tissue is, right? And from that, they can determine what your dose was at each of those levels. Okay. So these are the filters shown in the badges. They're inside of the badge. You would never see these without taking the badge apart. Dosimetry badges must always be worn facing forward. If they're facing backwards, then you're not going to be moving, the radiation won't go through the filter. The filters are placed between the source of radiation and the detector crystals or the film, whatever the detector is made of. But importantly, the badges are worn facing forward. They're worn at the thyroid level, so you wear them at your lapel, your collar level, unless it's a fetal dose badge, and of course you wear that at waist level. And I guess I do have time for this. The other type of badge is called a film badge. So TSLs or TLDs or OSL badges are the two common types. Again, remember, functionally they're the same. That's what's important. Film badges quite literally put a piece of photographic film in a sealed package. Remember William Rawlins, how he said, limit your amount of radiation exposure to less than that would fog a film in a day? Right? So remember, X-rays can expose film. The same principle is used here. Okay? The film gets denser, darker, okay, the more that the X-rays expose it. And you can use something called a densitometer to measure how much exposure was received at the film. So the densitometer, as it says, measures how dark the exposed film is by detecting the ratio of light that can pass through it. So I don't know if you've ever seen an X-ray, like piece of X-ray film held up to a view box, but bone looks pretty white, right? And like air and gas look black, right? The light passes through the air and gas easier than it does through the bone, and you can measure the amount of light transmitted through the film and detect how much exposure it's received. Now, there's big problems with film. The main problem with film badges is that they are very sensitive to moisture, heat, and light. So they're less accurate, and they're less durable too. On top of that, they have to be read out monthly because of all these factors. So you can't use them for very long. Where an OSL badge could be used for a year, film badges can only be used monthly. But they're cheap. That's the advantage to them. That's the only advantage to them is they're cheap. But yeah, you send it through your washing machine, done. Leave it in your car, done. OSL badges wouldn't have that problem. TLD badges, though, the ones that you guys have, those are sensitive to heat because remember, they re-emit their energy when exposed to heat, right? So those you can't leave in your car. Okay, so just think about it like this. Don't leave any badges in your car, right? Don't leave any badges where they don't belong because if it's either TLD or film, they are sensitive to these environmental changes where the OSL badges just aren't. But it's important to treat all badges as if they're sensitive and use them in the right ways. Great. We're getting to the end of this here. I'd like to talk, I think, just about two more things before I let you guys go, and it's just the other two types of detectors. One of them, and this next couple slides will sort of encompass what I need to tell you for both these two types of detectors, but these are referring to what are called gas-filled detectors. Yeah.
So, here obviously we're in school and you give us the badges quarterly.
Mm-hmm.
When we're out of school and, we go out in the real world,
Yeah.
do we have to be the ones who order them?
No, so your employer will order your badge for you. Yeah, so as soon as you get hired, you sign your enrollment or whatever, you get hired, right? That day they should order your badge for you. And until you have your badge, you'll use probably a provisional badge, or either won't do that or you won't take x-rays. And in some cases if you don't receive your badge for a while and still work, they can average your dose. They can tell you what you received just based on an average. So yes, your employer will get you your badge. Your employer is responsible to keep records of your badges, but it's your responsibility to keep track of things like your lifetime dose. And there will be a radiation safety officer, but in all actuality, it's going to be you that's responsible for keeping track of things. But yeah, no, they order it, they pay for it, they switch them out when they expire. Yeah, yep. Okay. All right, so gas-filled detectors. Remember, X-rays, particulate radiation can ionize matter, right? So that means the air in the room, that means a gas inside of a chamber can be ionized. And when matter is ionized, as you learned, electrons are freed, liberated from the atoms that they were connected to, okay? If you can take and put gas that is sensitive to specific energy levels inside of a detector, and you put a pin down the middle of the detector and run a positive current through that pin, which is not hard to do. You run a positive current through the pin, and you run a negative current through the walls of the detector. Any ionization of the gas will free an electron. That electron will be attracted to the pin, the positive anode pin, and when the electron hits that pin, a small amount of electric current is generated in the pin. Okay, small amount of increased electric current is generated in the pin, and you can read that amount of electric current as you would with any electric current. You can detect how much current based on how many electrons were liberated. The more electrons liberated, the more current runs through that anode pin. That's the principle behind gas-filled detectors. Freed electrons within the chamber of gas strike an anode plate, generating electrical current. This is the principle behind personal pocket dosimeters, as well as what's called a Geiger-Müller tube, or you probably just heard of them as called Geiger counters. Okay, this is the principle behind them. There's a chamber filled with gas. Electrons are freed, and they strike a pin generating current. Now, the pocket dosimeter, these guys, Okay, these are used by physicists, other radiation workers that work around, higher source, usually particulate radiation, and they need to measure their dose daily. Okay, so pocket dosimeters, ionization chambers, Geiger tubes, they function on what's called gas-filled detector principles. Now, the pocket dosimeter is kind of cool, so let me explain. It looks like this, looks like a pen. Inside of it, instead of having an anode pin, there is a small foil leaf. Okay, the foil leaf is what you can't see right now. Is the foil leaf is wide. It's wide along this axis here. Okay, it's wide this way, and there's a viewing port here. Let's see a little eyeball. Okay, there's a viewing port here. So when you look down through the viewing port, you're going to see a line. That line is the metal foil leaf. Okay, the metal foil. You're looking at the metal foil leaf on edge, and as gas is in here, as the electrons are freed from the gas, they're attracted to that metal foil leaf. Okay, that metal foil leaf builds up a charge and actually moves. That metal foil leaf moves. You can see that leaf move, and it'll move in the direction of increasing dose. Okay. And as the day goes on, you're working around you're a physicist, you're working around your source of uranium, right? Holding it in your hand, turning it about, right? As physicists must do, of course. And they are wearing their dosimeter right in their pocket, right here by their source. Some are, importantly, they're wearing it in their pocket. At the end of the day, they take and look at their dosimeter, and they go, oh yeah, look at that. I got 250 milligray today, okay? Be kind of a lot in a day, but they got 250 milligray today, okay? And they take that device and then they write down that number in their log, okay? They keep a log of these things. So no one's going to report this to anybody. These guys have to report it to themselves. They keep it in their log, they write it down. Then they take their device and they plug it in it's like an opposite of a charging port. It's a discharging port, okay? And then it gets discharged. The device discharges and it goes back to zero. The metal foil leaf just moves back to zero after the device is discharged. Then they pick their pen up the next morning, they stick it in their pocket, and they pull out another source of radioactive material and they work with that, okay? And that little metal foil leaf the whole time moves and moves and moves, detecting increasing dose, and they write that number down at the end of each day, okay? These work well for that kind of employment where you're getting higher levels, and you need to be able to accurately measure those higher levels, and I need to know like right now, today, what my dose is. I don't want to wait 3 months to know what my dose was because I could have gotten, damaging levels of radiation in that day, right? So these pocket dosimeters work well for that kind of employment. Great. The last thing that I'm going to discuss is what I've already prepped for, which is the Geiger-Müller tube. So this is an example of a Geiger-Müller tube. This handle with this circular end, that's the detector, right? The detector is that circle. They're highly sensitive, but have relatively low accuracy. They work great for detecting particle radiation. They do not work great for detecting electromagnetic radiation. They have a narrow range of energies they're sensitive to. Guess what they're sensitive to? They're sensitive to alpha, beta, and gamma radiation because that's what they're designed to detect. They're great for environmental radiation or contaminated surfaces or in nuclear medicine or labs, like we're going to do some labs, and they work great for that. So Geiger-Müller tubes. Geiger-Müller tubes take advantage of a type of gas called noble gas. Okay, what do we know about noble gases? Probably heard something about noble gases before. You guys like those neon signs that are outside of stores? Like open. Sometimes they're open signs, but other times like make really cool signs, right? Really cool structures. Inside of those signs, the color that you see is each one of those different colors is a different noble gas or a different mixture of noble gases. Noble gases on the very right side of the periodic table, those light blue gases on that right column, they're on that very right column of the periodic table because they're full. They can't take on any more electrons in their outer shell, okay? So noble gases are ready to ionize. Any energy dumped into a noble gas, it will eject an electron. What we got?
After class.
Got it, okay. So any energy dumped into a noble gas, it's ready to ionize and it'll free the electrons. So noble gases work great inside of Geiger-Müller tubes. The noble gas called argon, you'll see it the third one down on the right, Ar, that's argon. And argon's full. It can't take anything in its outermost shell, okay? And so it's easily ionizable. And that's and in most of these tubes that do this, there will be a noble gas, but specifically in Geiger tubes, it's argon gas that does this. And yeah, so those neon signs use noble gases because they emit pretty colors of light, and in Geiger tubes, noble gases work great because they're already full and they can just ionize very easily. So that's what makes them very sensitive. Part of what makes them very sensitive. With all that said, I could talk for longer, but I'm going to go ahead and call it a good day, okay? I'm not going to give you guys a quiz today, okay? I'm just going to say, get ready next time to take your final exam, okay? So we're going to test on these two chapters, perspectives on radiation and units on radiation the next time we meet, alrighty? Pause.